Some people wonder why I rounded to the whole nearest whole number. Again, technically, you always round to the nearest to the next decimal place. That's why when you do the this part of it, okay, the inequality, it does make sense that we rounded to an extra decimal place. All right, but then when you're writing it out loud, nobody cares about 52.3 days. That's kind of silly. So what you want to do is you want to just always round it to what makes sense. Because again, this is kind of what, if you were to publish something, this is what you would publish. The key is you always have to round down over here because this is a less than. So even let's say this changed to an 8, you would still round down to 52. Okay, and let's say this was a 2 instead of 7, you would still have to round up to 56. So when you go from decimals to whole numbers, you always go down to the left and up on the right. Okay, so basically this one you just always cross that off and then make that one more bigger. Okay, so here's our next one. Survey of 30 emergency room patients. So N is 30. The average waiting time is 174.3. So X bar is 174.3. Again, it seems weird that you would write 0.3 minutes, but if you remember clear back in chapter 3 when we were doing the calculations, like I just said, you're supposed to round to one extra decimal place. All right. Population standard deviation is 46.5. So sigma is 46.5. Find the best point estimate and the 99% confidence interval. So before I even start doing that, best point estimate, remember, is whatever the sample mean is. So the best point estimate is 174.3 minutes. So that part's done. Okay. Now we want the 99% confidence interval. So we're going to draw this out. Again, some of you probably don't need to draw it out, but I just like to. So this is 99, which means there's 1% left. So if this is 005, 005, because it needs to add to 1% or 0.01. So you're going to look in the big part of your chart again for what is closest to 0.005. Now, I can't zoom in very well, but hopefully what you notice right here, you have 0051 and 0049. Those are the exact same distance away from 005. All right, so what you have to do is you have to pick which one is going to be the bigger z-score. So not this one because it's bigger, but we actually use this one. And here's the reason, okay? Negative 2.5 is what row we're in. This one would be 257. This would be 258. So 258 is bigger. You have to think of the absolute value because, again, the z-score is always the positive one. Some books teach it that you actually split it in half. So you would do 2575, but our book does not. Our book says take the bigger one. Okay, and again, it's either 257 or 258. So we need to use 258. Okay, so if you messed up and wrote 2.57, then you're going to miss a half a point because, again, you need to use the bigger z-score. The reason, excuse me, that we have to do that is if you use 257, you might not be, you're technically not 99% then. So you actually have to overestimate rather than underestimate. Okay, so z of alpha over 2 is 2.58. Once you have that, then we use our formula. So 174.3 minus 2.58 times 46.5 over the square root of 30, less than mu, less than that whole thing with the plus sign. So again, most people, instead of writing it all out, just put the plus or minus sign right here. But again, you have to remember to write your answer as an interval, okay, as an inequality. So it's kind of up to you. If you feel comfortable not writing it all out, then that's totally fine. But remember, your answer is always two parts, inequality and then written out. Okay. So again, I want you to type this all in at the same time. I don't want you to take a break, enter something and round and all that. So 174.3 minus 2.58, parenthesis, 46.5 divided by the square root of 30, 152.4. And then again, this calculator is so nice because you just hit second enter, all that comes back, and just arrow over and change the minus sign to a plus sign, 196.2. Okay, so there's the first part of your answer right there. So this is technically your first answer, and then first part of your interval answer is that. So then you say you can be 99% confident that I'm going to write this one out, mean waiting time in the ER is between 152 and 197 minutes. So even though, again, technically you would round to 196, this is a strictly less than sign, so you need to round it up to 197. Again, you're not saying that every ER waiting time is between 152 and 197 minutes. That would not be good if it's a true emergency. This is if you could take and somehow find the population mean for the wait time of the ER. Okay, so and again, your population might be different. Maybe this is only at one certain hospital, but it's still pretty impossible to ask every single person that ever comes into the hospital how long they had to wait in the ER. So they found a sample of 30 people, and we're making our guess, our best guess, our estimate based on those 30 people. So we think the mean waiting time for everybody, if you could do that, would be between 152 and 197. Obviously, some people will wait way less than that. Some people will probably wait way more than that. But that is what we think that population mean would be if you ever calculated it. Okay, so those are two examples of your confidence intervals. So the only thing that will ever change for 7.1 is whatever this percent is. Everything else is going to look the same. All right. One last thing in chapter 7, in 7.1. This is if you know what you're looking for, you can figure out how small of a sample size you need, okay? Or at least what the minimum sample size would be. Obviously, the more you can get, the better, but this would be your absolute minimum. So the formula is n equals, because n is our sample size, big set of parentheses, z of alpha over 2 times sigma over e. That whole thing needs to be squared. Okay, so you're still going to have to do z of alpha over 2 like we've been doing. Sigma is your population standard deviation. E is your margin of error. So when you read through the problem, you're going to have to say, it won't say the margin of error, but hopefully we'll see what this means. So a scientist wishes to estimate the average depth of a river. He wants to be 99% confident that the estimate is correct, is accurate within 2 feet. From a previous study, the standard deviation of the depths measured was 4.33 feet. What is the minimum sample size needed to guarantee this? So again, figuring out how many samples of this river he's going to need to take. So z of alpha over 2 comes from the 99%. So I'm going to be naughty, and we already did it, so I'm not going to do it again. So z of alpha over 2 equals 2.58. Again, that's because we already did the 99%. Sigma is the 4.33. So the other number in there is 2, and you see this word within. That's the margin of error. He wants to be within 2 feet. So E is going to be 2. So n equals parentheses 2.58 times 4.33 all over 2 squared. And that's about 31.2. This is where people miss points all the time, as they leave their answer as 31.2. You cannot take 0.2 of a sample. Okay, so whenever asked for the minimum sample size, it has to be a whole number. So then the question comes, do we round it down to 31 or do we make it 32? You have to round up. Even though normal rounding rules would say that's 31. You're not going to get within your 2 feet if you only do 31. So you always have to round up. So minimum sample size is 32 readings. Okay, so no decimals allowed for sample size. You always have to round up, even if the rounding rules do not tell you to round up. All right, so that's it for 7.1.